Greetings Computing Conference 2020, conference chair and all participants. My name is Charles. I will be presenting a research submitted to this conference entitled False Asymptotic Instability Behavior at Iterated Functions with Lyapunov Stability in a Linear Time Series. I work nowadays at the Secretary for State of Education and Sport, a government institution at the Paraná State, Brazil. This is my poster submission, what you are viewing now, of the article submitted. I will be presenting now a better explanation of this research. The first main problem addressed in this research is to establish a difference between empirical experiments and theoretical mathematical simulations regarding asymptotic stability and bifurcation phenomena. Although asymptotic iterated functions can be often considered empirically invisible in their nature of proportionality and convergence, due to time-dependent outcomes and stability scenarios where high-level complexity is found in a given phenomenon, all the solutions in convergence to a dynamic and time-varying fixed point can be empirically visible if time nonlinear lengths of phenomenon can be accelerated by mathematical tools or physical properties in connectivity with the event. This research practical implications is to empirically predict how physical phenomena will behave in very complex scenarios for many fields of science, and also mainly for policy making regarding descriptive statistics and methodological limitations in the big cities administration. The main result of this research dealt with a simple example, using nonlinear time series data where an approach for qualitative theory of differential equations techniques were done, giving a general overview of time-varying solutions convergence at no autonomous partial differential equations. Classifying detecting nonlinear events behaviors towards iterated high-order functions can be challenged due to probabilistic random outcomes. Mostly nature phenomena present oscillatory dynamics in which detection results in nonlinear time series that express high complex trajectories. This research wonders what if the nonlinear time series present an orientation to a fixed point over time. We are not talking about little time of analysis but a very big time. Some phenomena might express outcomes with a desired behavior in a very short time period, while others can express the same desired behavior in a million of years. For this limitation problem, we need simulations or other tools that can predict how a phenomenon behaves over time and extend it beyond our own life existence. What this research proposes is a design framework of analysis for high-order functions behavior over time, where one cannot prove that some phenomena might not have fixed point attraction if time is the limiting factor of he or she research, and time here reflects directly your data samples, or in other words, your empirical observation of an event. One first conclusion of the theoretical research conduct was to demonstrate that in nonlinear time series analysis, the asymptotic instability observed with the empirical datasets, if time accelerated, this filter reveals itself as an asymptotic stability behavior oriented by an attractive distribution. One technical conclusion arises from it, and in the result session as well, is about when investigating the empirical behavior of complex events, many conducted experiments can also fail when trying to identify the asymptotic stability behavior on events, mainly defining this asymptotic stability behavior as unstable, unpredictable, and without any prior pattern formation. This point leads the methodology proposed in this article as an observation to most scientific data concerning fixed point stability that is disconnected of empirical data sets over time. A second conclusion states that considering that iterated complex variables can possibly not present a pair formation for short time lengths, the average distance between fixed points is also followed by a low rate of convergence, that is instability. That in terms of scientific interpretation can be understood as the phenomenon not presenting a high level of interaction expected to be in convergence to any given and predetermined fixed point, but oriented to an predictable behavior of the event. Though these interactions are also existent, in the extent of time of empirical observation be enough greater than the periodic time in which complex variables were observed, possibly leading this to a new stability pattern and therefore to the concept of dynamical fixed point existence, same as happens with law of great number physical properties and monotone functions as well. This could lead to the statement that if a phenomenon presents a very high level of complexity, the outcomes of convergence can also present higher time periods to be able to expand it into a new degree of pair formation. These useful time varying patterns of convergence and no convergence at specific time lengths can be useful for many theoretical and empirical research for atmosphere nuclear particles collision and intelligent cities, epidemiological models outside SRR limitations, and many other fields of knowledge. I thank you all for watching this video. And here is my contact. I am open for any inquiry regarding the research submitted. I believe the presentation and the poster submission will be presented in the website of the conference as well. And I'm waiting for any comment that any research might want to send. Thank you very much all for watching.